Hello! We have a problem that looks at the relation between geometry and optimal solutions. We have a linear program here where the constraints are written in the form ax is at most b, the standard form for a polyhedron. Also note that this LP is derived from standard equality form. We put the non-negativity here in the last two constraints. The feasible region is drawn here. And there is an arbitrary vector c in the objective function. There are four extreme points in this polyhedron: 0, 2, 2, 0, 4, 0, and 6, 1. There are four parts to this problem, and we will go through them one by one. First, we will write down the cone of tight constraints for each of the four extreme points. Recall that each extreme point is defined by setting some of these constraints into equality. These are the tight constraints. The cone of tight constraints is all the non-negative combinations of the normal vectors of these tight constraints. For 0, 2, there are two tight constraints as shown here. The normal vectors are -1, -1, and -1, 0. So the cone of tight constraints is the set of lambda 1 times -1, -1 plus lambda 2 times -1, 0 for all non-negative lambda 1 and lambda 2s. And we can do a similar thing for the other three extreme points. For 2, 0, we have the cone generated by -1, -1 and 0, -1. For 4, 0, we have a cone generated by 1, -2, and 0, -1. And for 6, 1, we have a cone generated by 1, -2, and 3, -1. For the next part, we have some possibilities for the vector c in the objective function. And for each of these vectors, we want to find one possible optimal solutions of the LP. And the result from class that we are using here is that a feasible solution x bar is optimal if and only if c is in the cone of tight constraints for x bar. Also, for polyhedrons derived from SCF, if there is an optimal solution, then there is an optimal solution that is an extreme point. Try to explain why that is. So in this case, where we are trying to find an optimal solution for each c, we can limit our search space to the cones of these four extreme points. For the first c, which is -314, -1, we see that the vector goes like this, and it looks like it is in a cone for the point 2, 0. We can verify this algebraically. -314 -1 is 1 times -1, -1 plus 313 times -1, 0. These coefficients here are non-negative, so our vector c is indeed in the cone of the tight constraint for 2, 0. So 2, 0 is optimal for this particular c. And we can do similar things for the other two c's. For c equals to 3 -1 for 1, it looks to be in a cone of 4, 0. And we can check this algebraically with this non-negative combination of these vectors. So 4, 0 is optimal for this c. For c equals to 31 -41, it is in a cone for 6, 1. And we can verify it with this equation. So 6, 1 is optimal for this c. For the next part, we want to know what can you say about the outcome of the LP for a vector c that is not in any of the four cones of tight constraints that we have here. Well, if c is not in any of the four cones, then no extreme point is optimal. So by our argument in part B, this means that no optimal solutions exist. That's because if there is some optimal solution, then one extreme point must be optimal. But the LP is feasible, so we have a linear program that is feasible but has no optimal solutions. By the fundamental theorem of linear programming, that means that the LP must be unbounded. And finally, we want to know, is there a vector C for which 3, 2 is an optimal solution? Now from the diagram, we see that 3, 2 is in the interior of the polyhedron. In particular, there is no tight constraint for 3, 2. That might suggest that there is no possible C for which 3, 2 is optimal. However, there is still a cone of tight constraints for 3, 2. It is the cone generated by no vectors, which is the set that consists of just the zero vector. So our theorem tells us that when C is 0, 0, 3, 2 must be optimal. Let's verify that. When C is 0, 0, the objective value is 0 for any feasible solution. So in fact, all feasible solutions are optimal. And that completes our problem here.